So the second one of these was a shadow question. And I told you there's two different kinds here. There's one where there's a light post, like a lamp is in the air shining down, and there's a light on the ground. There could be a second version of this where the light's on the ground shining at someone and their shadow's going to end up being on the wall here. This is one where there's a 40-foot tall lamp post. Okay, so in the middle of the dark night. That's not important, but I'm going to underline it anyway. So the 40-foot lamp post means there is a lamp that is 40 feet tall. There it is. Boom. And I'm going to write 40 there because it's not changing. The lamppost isn't changing. The lamppost is just kind of hanging out, shining, you know. And here's the ground. And there is a man who happens to be a 5-foot tall man, actually, right there. He's hanging out over here somewhere. Now, I know this is not to scale, if that's 40-foot lamppost and that's a 5-foot tall man, but give me a break. And the light is shining, and this guy's blocking the light over here, creating a shadow. So this is the guy's shadow right here, which I'm going to call H. That's this length right here. Cool. And just to make this a nice little triangle, we're going to go up there. Now the light, again, is shining all over the place. It's just doing its thing. Shining, 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 shining. Okay, so it's all lit up. But because the guy's standing right here, he's blocking the light, creating his shadow right here. Okay. We also happen to know that he's moving away or toward, where are we at here? He's toward, right here, bam. He's moving toward the lamppost. That means he's moving this way. That means this measurement right here is shrinking. I'm going to call it X, but I know that it's getting smaller because he's moving towards the lamppost. Okay? So I'm giving you, in this question, how fast he's moving. He's walking at 4 feet per second. Well, if he's walking at 4 feet per second, that means X, every single second that goes by, is getting smaller by 4 feet. That's the rate of change of X. That's dx dt. Dx dt is -4 feet per second. It's negative because it's getting smaller. He's walking towards the lamppost. If he was walking away from the lamppost, then X would be getting bigger and it would be +4. Now, that's a rate of change that we know. The rate of change that we want to know is how fast is his shadow changing. Well, because I'm calling his shadow H, what this question is asking us is, what is the rate of change of H with respect to time? That's what we want. So we have to try, our best bet here is to connect the rate of change we know, dx dt, to the rate of change we want, dh dt. So to do that, we're going to use similar triangles here. We have to find an equation. So when I say we have to link them, I mean there has to be an equation that has both of them in it. And the equation that links X and H, if you look at these two triangles, look at this little triangle here, right here. We have the side here, the vertical side, which is 5, and the horizontal side, which is H. So what's nice about similar triangles is that their sides have to be proportional. So if I were to take the horizontal side here and divide it by the vertical side there, 5, then that has to be the same exact ratio, fraction, as if I have to take the whole big side here, the whole big horizontal side, divided by the vertical big side. So that means the horizontal, the big side, is X and H together. Okay? We're adding them because if H were 10 and X were like 50, well then they'd add up to 60. That's how long that side would be. I don't know what they are though, so the best I can say is that it's X plus H. And that's over 40. Okay? And again, this equation must be true because of similar triangles. And we can derive this the way it is, but I told you in class it's a whole lot easier just to cross multiply here. And then simplify it down so we can combine our h's. There's a 5h over here, so you can do minus 5h here, minus 5h here. And we find out that 35h must be equal to 5x. Okay? And that's the same exact equation as right here, just a whole lot easier to look at. Now that doesn't tell me anything about the rates of change. It just tells me how the relationship has to be. But because of the, the laws of nature and the rules of calculus here, because that equation must be true, if I were to derive both sides, that equation that results from that must also be true. So if I derive the left-hand side, the 35 is just kind of chilling, and you get to derive h, dh dt. That must equal 5 times the derivative of x with respect to time, dx dt. Those two things have to be equal. And if you remember from way, way back here, we already know what dx dt is. Dx dt is just negative 4 feet per second. So in this equation, we can just go ahead and rewrite it, and I can plug in what dx dt is, negative 4 feet per second. And that allows me, awesome, goodness gracious, to solve for dh dt. Well, 5 times negative 4 is negative 20. And we're going to have to divide by 35 to solve for dh dt. So it's negative 20 over 35, which we can reduce by canceling out a 5. So that's negative 4 over 7. And that's the rate of change of the shadow. But we got to put units on there. Well, the shadow was measured in feet because that's what we measured everything in this question in feet. So the shadow also was measured in feet. And the rate of change of the shadow then must be feet per some unit of time. And because we're using per second in the rate of change of x, then h must also be in that unit. So it's negative 4/7 feet per second.